Hi folks, so today we're going to be looking at geometric series. So yesterday we did arithmetic series. Geometric series are the same, so we're going to still look at geometric sequences, something like 2, 4, 8, 16, where there's a common ratio. Okay. But this time we're going to start adding up the terms in the sequence, and that's what makes it a series. Okay, so there are two formulas that we can use for geometric series to be able to find the partial sums. They are these two. They're very similar. They're both in the formula book. And honestly, both can work in all contexts. The first problem, or the first formula, is most helpful when you have a common ratio that's greater than 1. Okay, the reason being is eventually you're going to do this value to an exponent, and then you're going to remove 1 from it. So you're only going to be working with positive numbers. Same thing here, okay? In the second partial sum equation, it's best when the R value is less than 1, because then you're going to be removing a small decimal or fraction value from 1, and again, it just allows you to only be working with positive numbers. Okay? And there is, I'm trying to figure out where it is. There is a full derivation, kind of like we saw on yesterday's, where someone looked at the pattern, put one sum in one direction, one in the other, and they subtracted these two, okay, to generate this formula, and then they isolated for the sum of n, and that's where we generate this. Okay, and we can multiply by a value of -1 over -1 to get the other formula. So these were generated through a derivation. Okay, so we're going to use these two formulas to solve the following 4 problems. So the first says, can you find the sum of the following geometric series? Okay, so in this case, I would always start out for any of the problems that involve a sum and a geometric series. The things that you need in all of the formulas are, what is your U1? What is your N? What is your R? Okay, if you have those pieces of information, you can always do the calculation. So our U1 is our first term, that's 2. Okay, our common ratio, if we look here, each term we're multiplying by 3 to get the next term. So our common ratio is 3. And n is the number of terms in the series. So we have 1, 2, 3, 4. So n would be 4. And obviously, we could very much just take this and add these 4 numbers. I'm just using it as an example of how we could use the formula. So because my R value is greater than 1, I'm going to tend to use this formula. Okay, so if I start plugging it in, I'm finding the sum of the first 4 terms. Then I'll take U1 times the common ratio to the power of 4 minus 1, all divided by 3 minus 1. So this calculation is going to become 2 times, and this is 81 minus 1, so 80 divided by 2. So the sum of the first 4 terms is 80. And in this case, we could actually validate it by just adding these up and making sure we get 80. For the second value here, or the second example, we're looking for S of 12. So the sum of the first 12 terms, and we don't have all 12 of the terms. So again, let's figure out if we know 1, the first term, if we know the ratio, and if we know the n value. So again, the n always comes from the value that's the subscript in the sum. So it's saying I want to only know the sum to 12 terms. So n is 12, our first term is 1, and it looks like we're multiplying by a value of 2 each time. So once again, because the common ratio is greater than 1, I would use this formula to be able to calculate it. So when doing that, it's going to become the sum of 12 is equal to 1 times 2 to the power of 12 minus 1, all divided by, 2 minus 1. So you would most definitely get a calculator. You would end up with 1 divided by 1. Okay, Okay, so it would really just be 2 to the 12 minus 1. So that's 4,096 minus 1, which is just 4,095. So those are two basic problems. Now, again, the goal is, can we find the sum of the geometric series? But you'll notice this time, it doesn't tell us what the n values are. Okay, so as we're doing this problem, it's going to be a task that we need to start by figuring out what n is, and then we can go into filling the formula. So I always suggest, if your goal is to find n, I would go back and use the general term formula that we were using in the previous sections. Okay, and you can use any value. Okay, I'm going to use the fact that we want to know the last value, because we want to take the sum all the way to that last value. I would treat this as your un. So I'll put negative 8,192 is equal to, the first term is 4, and the common ratio, well, between the first and the second term, I'm multiplying by negative 2, multiplying by negative 2, so the common ratio would be negative 2 to the power of n minus 1. And now the goal is to solve for n, so we could divide both sides by 4. Okay, if you had access to technology, you could find the intercept. We actually could even create a common base using our knowledge about exponents now. This would be negative 2 to the power of 11. Okay, so that would be an option. You could create a common base of positive 2 as well. Okay, and then we could set the exponents equal to each other, and we would discover that negative 8,192 is the 12th term. Okay, so that means we're really trying to find the sum all the way until the 12th term. So I'm just going to write down, we said the r value was negative 2, and the u1 value was 4, and our n value is going to be 12. So because the r value is less than 1, okay, I'm going to tend toward using this formula. Again, it's just to help not have to deal with negative values as you're doing the calculation, but it's not the end of the world if you do use the other formula. You're just going to have to be doing calculations with negatives. So it'll be u1 times 1 minus the r value to the exponent of 12 divided by 1 minus negative 2. So 1 minus negative 2 to the 12, that's going to end up giving us that negative 4,095 and a denominator of positive 3. And I plugged this in as just one big calculation and got negative 5,460. Okay. In the second problem here, it's very similar, but we're going to be working with some fractions, which is really good to continue practicing. So to get from 1 to 1/3, I'm multiplying by 1/3. And let's just validate, if I continue 1/3 times 1/3, that gives me 1/9. So our common ratio is 1/3, and our u1 is 1. Again, this time we still don't know n. So before we start, we need to plug in to our general formula over here to be able to figure out what n is. So I'm going to treat 1 over 243 as my un to figure out which term is this. So u1 is 1, the r value is 1/3. I'm just going to remove the 1 there because it's not really needed. And we can again actually create a common base of 1/3. Okay, and that would be to the exponent of 5. If you wanted to change this to be 3 with an exponent, that works as well. So we'll get 5 is equal to n minus 1, or 6 is n. So this is the 6th term. So we're looking to find the sum of the first 6 terms. Because my r value is less than 1 again, I would still use this formula, even if it's a decimal or a fraction. So it would be my first value, my u1, times 1 minus 1/3 to the power of 6, divided by 1 minus 1/3. Okay. I'm going to do it out with fractions, but if you didn't, or if you did have access to the calculator, you wouldn't need to. So in this case, I'm just going to, this 1 is not really affecting. It's just multiplying by 1, so I'm going to just leave it as 1 minus, and 1 over 3 to the power of 6 gives us 1 over 729. And the denominator, well, a 1 is really like a 3 over 3. So it's a 3 over 3 minus 1/3, so 2/3. So in my numerator, this 1 would be 729 over 729. So I'd end up with 728 over 729 divided by 2/3, which I could rewrite as 728 over 729 times 3/2. And you can always simplify your diagonals if you want. So for instance, I noticed that 728 and 2 are both divisible by 2. Okay, so that can help simplify your calculation if needed. But again, if you had access to a calculator, you could end up generating 364 over 243. Okay, and that would be the simplified fraction. Would you be able to write this as a decimal? I would have a tendency, because the original was written as a fraction, to include the final answer as a fraction as well. And that way it is an exact answer. Especially if the question says exact, it would expect a fraction. And our last problem here. So it says, for the series 3, 9, 27, what is the minimum number of terms needed for the sum to exceed 1,000? Okay, so this one, it doesn't even say what kind of series it is. So you would actually have to start by determining, is this arithmetic or is it geometric, before you get into any work. So in this case, if I look at 3 to 9, well, I'm adding 6, and I'm adding way more than 6 there. So if it's a ratio instead, I'm multiplying by 3, I'm multiplying by 3. This is most definitely geometric with an R value of 3. And I'll just write down that I have a U1 of 3, and that the goal is to figure out n, because n is the number of terms. So in this case, we could start filling in the geometric sum. Okay, so if I fill it in, because the R value is greater than 1, I would again use the formula where it's going to be the R with an exponent minus 1. So if I fill it in, it's going to be 3 is equal to 3 to the power of n, because that's unknown, minus 1, all over 3 minus 1. And this is how we're finding the sum of n. And we're asking ourselves, when is this greater than 1,000? When does it exceed 1,000? So I would even have a tendency to change that to be, when is this greater than 1,000? You could also solve it with an equal sign and find when are the two sides equal to one another. Okay, and now could find the n value, a little bit like on our test that we did recently. So if we start calculating a little bit, we're going to get a 2 in the denominator. If I multiply both sides by 2, I have 2,000. And then if I divide both sides by 3, I have 2,000 divided by 3. And I'm going to add the 1 as well. So if I add a 1 to both sides, this is really going to be like I'm adding 3 over 3 on the right-hand side. So I'm going to write, that's 2,003 over 3. Okay. At this point, you could either use your calculator, put this under y1, y2, see when they're equal. You could have done that right from the beginning. Put this under y1, y2, see where they're equal. You could use logarithms. So you could change this into logarithmic form to say, well, n is greater to log base 3 of 2003 over 3. Okay, all of those strategies would absolutely be correct because this would be a paper 2 question. Okay, so if I plug this in, I'm going to get an n value. It goes 5.92, and it does continue. Okay. And because we're talking about the number of terms, the number of terms has to be an integer. We don't have a partial number of terms. So the next value, when it's finally going to exceed, is going to be at 6. So I'm going to say the minimum number of terms when the sum exceeds 1,000 is 6. And I am going to put here the calculator would have been an absolutely appropriate strategy as well. Okay, folks, that's it for geometric. Best of luck, and I will be back Monday. Have a great weekend.